going to take the whole period, but we're going to finish up the section on solutions. And before we get into solubility, how solutes dissolve in solvents. In the last class, we covered up through the dissolving of solid solutes into solvents, right, to form solutions. So we talked about ionic solvents and ionic solutes and covalent solutes. So both cases of solid solutes. That's probably the key. Last time we spoke about solid solutes. Today we're going to talk about liquid solutes and gaseous solutes for a little bit. And but the principle behind them all is pretty much the same. What are the points that you had from the last class in terms of solid solutes dissolving? What are the key things that you recall from Friday, if you recall from Friday? I'm assuming that everybody turned in review questions 1 and 2 as well. If you haven't, I don't say fess up, but technically today's was really light. It would take you just a few minutes to step aside and do it. But in the future, if there's more intensive homework, you're not going to be able to just step out for 10 minutes and catch up. But in the idea of solid solutes, what were your takeaways? What do you remember? What were the key points? If someone weren't here, say someone had to go, hypothetically, someone had to go watch it on YouTube, right? What should that person make sure that they get from that YouTube video with regard to solid solutes and how they dissolve? We had 2 cases, right? Ionic and covalent solutes. Maybe the phrase solute still bothers you a little bit. What is a solute, for review?
Substance we are dissolving.
Okay, so we said in the typical paradigm, we're going to talk about, generally we think of a liquid solvent and a solid solute, like salt being put into a glass of water. That's kind of the paradigm we think of, most people think of first of all. So we take the solid salt, we pour it into the glass of water, we have salt in the water, we're going to dissolve it. How do we typically think about dissolving it? What are we going to do? Stir it up, right? If I gave you water and salt and said, here, make salt water, you put the salt in it, okay, you hand it back to me, I'm like, okay, close. Let's actually get the salt into solution. Let's get that solute, salt, into the solvent, water. Let's mix it up and form that solution. Then we have salt water. We mix it up. Okay, so we think about a liquid solvent, but remember the solvent doesn't have to be liquid. And we have a solid solute, but remember the solute doesn't have to be solid all the time either, but that's generally the way we begin to understand it. When we look at a crystal of, in this case, salt, we have to remember that does it or does it not represent a molecule of salt? 1 grain of salt, is that the same as a molecule of salt? No. See, most of the heads moving. No. That grain of salt actually represents many, I don't want to say thousands or millions, but it's a huge number of actual molecules of salt that is in that grain of salt. When you see that grain of salt and you put it in water, and it's still in the water, in order for it to disappear, what we need to do is separate that block of salt into individual molecules of salt, or in the case of an ionic, it's actually not going to break down into molecules, it's going to break down into the ions, right? So we put something like salt that's an ionic compound, an ionic solute, into water and mix it up. Because it's ionic, it will break down into individual ions. That's different than putting a covalent solute into a solvent. What happens when I put something that's covalent into a solvent and mix it up? What is dissolving? How is dissolving different between an ionic compound and a covalent compound? Covalent compounds don't break down into individual ions. They don't break down if you think of it as a decomposition reaction, the individual elements, the molecule doesn't go through a decomposition into individual elements or individual ions. It can only break down to the molecular level, to a molecule. Okay? So NaCl, sodium chloride, that's a sodium ion and a chloride ion that are stuck together by this attractive force of opposite charges. They're stuck together, but there is no, we call it a physical bond between them. Water can come in and can relatively easily separate them and get between them. Whereas, I think they use a pH3 molecule as the example in the book, that molecule has covalent bonds. We call those physical bonds. We say that water comes in and it doesn't have the ability to break up the bonds between the elements that make up the molecule, but it does have enough strength to break the connection between the molecules, one molecule and another molecule. So remember, the takeaway is that for a covalent solute, the solvent can break it down to the molecule, but no smaller. For an ionic compound, it can break it down into the individual ions and separate them. Now, this whole act of dissolving is based upon charges. Okay? So we talk about water as a solvent, sodium chloride or pH3 as a solute. We actually get down into the nature of the solute and the solvent and how they interact with one another. Remember, the greater principle is that polar and nonpolar, that they dissolve like. A polar solvent will dissolve a polar solute, and a nonpolar solvent will dissolve a nonpolar solute. The classic example of that is two liquids. When you have grease on your hands or oil on your hands and you try to wash it off with water, water is polar, the oil is nonpolar, and no matter how much you wring your hands underwater, the grease doesn't come off. You've got to get a soap involved, right? You've got to use some other agent that's going to get get the oil off your hands. And we've mentioned before that the nature of a soap is that it's a long-chain molecule, and on one end it's polar, and then the other end it is nonpolar. And so it has the ability to act as both. It gets in there and is able to take advantage of that nature. Basically dissolve the grease on your hands, and at the same time the water can wash it off. So that's part of the nature of polar and nonpolar. But both of those cases we talked about solids. A ionic solid or a covalent solid. Part of moving forward is to recognize as well, though, that we don't always have a solid solute. We can have a liquid solute, and we can have gaseous solutes. So if we return back to, remember, we talked about the kinetic theory of matter. Okay, this is where we go back to other portions of our learning. The kinetic theory of matter, and when we learned that, I said, do solids, like a solid, different elements, we have a pure substance, we have a block of one of our elements, we say it's in the solid form, the solid phase. How did I describe the relationship between atoms, or it could also be molecules, in the solid phase? What is their relationship like with one another? And I'll give you a hint visually, because I did it visually. What do they do with relationship to one another? Sure. In the solid phase, when two atoms or molecules that are beside each other in the solid phase, are they moving? That's the way I phrased it before. If they're solids, are they moving? We talked about the kinetic theory. Is that empty desk, well, that one's, your feet's on it. Let's say this flag, is it moving? Are the molecules of the flag moving? Yes. Every molecule, every atom is moving. What's the relationship between the atoms of a solid? Let's maybe think of the stick, because maybe the slight breeze in here messes you up. But the solid stick, we tend to think of a solid as not moving. But actually, kinetic theory of matter tells us that the molecules and the atoms are moving, but they're moving by vibrating, right? So even though there's a net zero motion, this textbook right now, all of the atoms and molecules that make it up are moving. There's a net zero motion. Why isn't this thing just slowly vibrating off and falling on the floor? Well, because as there's a set of molecules or atoms that are moving in one direction, other atoms or molecules are moving in the other direction, and they're offsetting each other all the time. And so the net result is no motion. In the same way that a positive and negative charge both coexist, and yet the net charge is zero. Remember we'd say, for example, does a zero charge mean it has no charges? No. A zero charge means it's perfectly balanced. Whatever number of negatives it has the same number of positives, and so they balance out to be zero. In terms of motion, a solid has motion in all directions, and the net resultant motion is zero because all the submotions offset each other. So we refer to solids, two molecules of solids being next to each other, as vibrating. They're vibrating back and forth like this. In dissolving a solid, what we're really talking about is water, in the case of sodium chloride, but for anything, a solvent, to dissolve a solid, it needs to have enough force to get between and separate the vibrating molecules, or the vibrating atoms. In the case of sodium chloride, the two ions, sodium and chlorine, they're vibrating. They're solids. They're in relationship because of opposite charges. They're attracted to one another. The solvent has to get in between them. Once it gets in between them, what does it suddenly look like? Remember the different phases? We talked about solids. What's next? What has a little bit more motion than a solid? Liquids. And the way I demonstrated liquids was to take my hands and to start wrapping them on each other, right? They're touching, they're in close proximity, but guess what? There's a lot more freedom, there's a lot more motion and movement here. Okay? When you have a solid and then a solvent gets in between them and separates them, suddenly there's a higher degree of motion, higher degree of freedom that takes place. So though we tend to think of a solid solute and a liquid solvent, we can have, for example, a liquid solute. Liquid solute, one other way to say that is just simply dissolving a liquid in a liquid. Since you have, in the liquid phase, liquids are in motion, if I add other molecules that are also likewise in motion, how difficult do you think it is to dissolve it? It's not difficult at all, right? It's relatively simple compared to the solid. Now you may want to, if you have a liquid dissolving in a liquid, you pour the two liquids together to make a mixture, right? You might say, hey, I want to have a homogeneous mixture, so I'm going to stir it up. But the interaction and the exchange, the placement or displacement of the different atoms and molecules happens very, very easily and very, very quickly, as opposed to a solid. Again, sodium chloride goes into water, it's going to sit there. You have to stir it up maybe, or you've got to get more motion going, so you may heat it to get the water moving more. It'll stir, that stirring will cause the more of the water to interact with the solid, and because of the charges, be able to come in there and separate out those ions. I pour a liquid in there, and it's immediately starting to dissolve. It's already starting to have molecules of one and the other get between each other. You may decide I want to take a spoon and stir it up so that it's the same consistency everywhere. Okay, but that isn't as crucial as it is for a solid, because the interaction between them, the dissolving action, is going to happen almost immediately with a liquid and a liquid. So since they're already relatively far apart for a liquid, if you think about not just their motion but their proximity, if you think about gas or solids as being tight together, liquids as being close together, and gases are far apart. That's the way we tend to think of them: solids, liquids, and gases. So to get other molecules between them goes from difficult, it would appear to be much easier in a liquid, right? But that doesn't continue on to the gas phase. That's why if you look at your notes, there's so little, maybe page 354 covers both liquids and gases. Because the real paradigm you need to learn is how does a solid dissolve? And from there you can make other associations. So a solid is a little more difficult to dissolve, And everything we talked about in the last class applies in dissolving a solid. Dissolving a liquid is often just about getting them together. And by the nature of being a liquid, the molecules are already far apart. They're already pretty free-moving. And so get something together that's far apart and free-moving with something that's far apart and free-moving, there's not a whole lot of work on our part to make it happen. They may not need our help at all in order for the liquid to dissolve in a liquid. Again, this is a section where they get back into likes dissolving likes. That polars dissolve polars and nonpolars dissolve nonpolars. And that's more significant for liquid to liquid. The example I use with grease and water is a liquid-liquid dissolving. Okay, that's the example. The one that kind of throws the whole paradigm out of whack is this idea of gaseous solutes. A gaseous solute, where I'm taking a gas and I'm dissolving the gas into a liquid. Remember, the solute is the thing being dissolved. The solvent is the thing it's being dissolved into. And the solution is the result of the solute being dissolved into the solvent. To dissolve a gas into a liquid is very different than the solid or the liquid being dissolved into a liquid. If you notice the table over on 355 on the top, it kind of highlights this. Solid. In order for a solid to dissolve, you see you've got the different phases and then the requirements beside it. In order for a solid to dissolve, the solvent molecules must be attracted to the solute molecules so strongly that the solvent molecules get between the solute molecules and pull them apart. Again, that's everything we covered in the last class. The solvent molecules are able to get in between and pull the solute molecules apart. For the liquid, the solvent molecules need to be attracted to the solute molecules only a small amount, because the solvent does not need to separate the molecules very much. The solvent merely needs to get between them. So this one is not so much about the force of the solvent to break up the solute as it is of the presence of the solute to be in between, or excuse me, the solvent to be in between the solute molecules. It's giving it the opportunity more than it exerting its force. But notice the gas. This is the flip. The solvent molecules must be attracted to the solute molecules enough to pull the solute molecules closer to one another. There's the difference. From a solid and a liquid, we're talking about separating them, right? We're talking about making them farther apart. The solute has to be farther apart for it to dissolve. But if the solute is a gas, the solvent has to be able to pull them closer together. Let's think about that. When you think of a gas dissolved in a liquid, what comes to your mind? Where do you know of gases that are dissolved in liquids? Do you know of any? Okay. Classic example I think of is, now we're going to debate over this, right? Is it called soda or is it called pop? Or is it just Coke?
Both.
That's what it's in the South. It's Coke, right? Everything's Coke. Both?
Soda pop.
Soda pop? Okay, soda pop. Go to the machine and buy a soda, right? You open it up. Suddenly there's this change of pressure. There's pressure in the can, you open it up, pressure is released, you pour out the soda. How can you tell if it's fresh? It fizzes. As you look at the glass, it's bubbling. You notice on the Super Bowl commercials or any commercial about soda, they show that close-up of the glass. It's got ice in it, right? And you watch the bubbles, and they're moving up, and they're coming to the top, and they're releasing this gas. What you're seeing is gas coming out of solution. Where did that gas come from? Where's that fizz come from? It's gases that were in the soda. It was in the liquid. There were gases in the liquid that now, because of the change in pressure, are coming out of solution. So it's kind of like the reverse of dissolving. They're undissolving. The gas is coming out of the liquid. Before it was in the liquid, now it's coming out of the liquid, and when it comes out of the liquid, then it has a lower density, and it rises through the liquid to the top and pops. And if you get it real close to your head, it tickles your nose and Makes you like you're going to sneeze, right? Or you drink it real fast and you burp, right? Because you took all that gas in that was in the liquid and now needs someplace to go. So when you think of dissolving a gas, think of soda. There is gas in that. Now when it's capped, it's under pressure. The pressure helps hold it in solution. You don't see the bubbles. When there's a pressure differential, it comes out of solution. You can also affect it by temperature. We'll get into things that affect solubility. Temperature is one of those things as well, which is why a cold soda and a warm soda, they taste differently. And part of it has to do with how the gas is being held in solution. See, with chemistry, you can take all the fun out of just about everything, right? Next time you're drinking soda, like, okay, let's think about the solubility of the gas. Let's think about the carbonic acid that's in the soda, the burn that I'm going to feel when I drink it because I'm drinking acid. How my stomach's going to neutralize that acid with base. And at the same time, it's got gas in solution. And the process of putting the gas into the solution is what makes the acid that burns. Okay? But you don't drink it without the burn. You don't drink it without the bubbles. Why? Is it really appealing, you think, to have an advertisement with a soda glass with ice in it, and you pour the soda, and nothing happens? Why not drink Kool-Aid, right? It's not soda. It's different. And if you take a soda that has all these bubbles and you leave it out long enough, eventually, virtually all, if not all, of the carbon dioxide is released out of it. Does anybody want that? What do we call that when soda has lost all of its fizz? It's flat. It's flat soda. Nobody wants to drink flat soda. So you actually want to have some of that gas still in solution. And when that gas is in solution, then that fizz that you feel when you drink it is because of the changing parameters, the changing system, the gas is now being released. Rather than being released in the glass, it's being released in your body. And that fizz feel that you have going down your throat is the solution losing the gas that's in solution. It's coming out of solution and being released. But here's the point. For that carbon dioxide to be in soda, we're going to use that as our example of a gaseous solute in a solvent to form a solution. So Coke is a solution. It is a homogeneous solution, right? Because it's the same. Top of the cup doesn't taste different than the bottom of the cup. It's the same throughout. And in that solution, one of the things that's in there is a gaseous solute that's been dissolved into the liquid. No one deducted one to joke. That stretch, it's back there, trying to avoid your hands. Or were you trying to hit him? So anyway, but you've got this gas. How do we get it in there? Well, if you have a liquid and a gas, just think of it. We have a beaker. If I told you I had a beaker here, that I put a lid on, I closed it, and that inside of it, now granted, I'm just going to show this, put a line, the squiggly line, not that there's waves going on in there, but just to say, hey, it gives you the idea that there's a liquid. If I told you there was a liquid and a gas in there, I think if I just pointed that way, you came up and said, okay, there's a liquid and a gas, where are they? We would by nature say, well, this is going to be the liquid, and this is going to be the gas, right? If you just know there's liquid and gas in a beaker, how would they lay out? You would go liquid and gas. If I told you that I had gas in solution, where would be the liquid and gas? They would both be in what appears to us to be the liquid portion. The gas would be dissolved into the liquid. Yes, sir? Okay, you almost made it an hour. You may. Be more productive use of your time between classes. So you've got a gas in a liquid. The gas is dissolved in the liquid. What had to happen? Well, the nature of gases, remember, is that they are far apart. They're moving. A lot of dynamics going on here. They're moving around. If I were to tell you that I've got a hose and I'm going to bubble a gas through this liquid, okay, just stick something from your aquarium hose, in the liquid, I'm going to blow or place a gas in that liquid. What would you expect to happen? As the hose I place a hose here, and I force air in at this end, or whatever we're trying to dissolve. I send the gas in this way. What's going to happen at the other end of that hose? Start bubbling, right? And you would anticipate that they would bubble up till they pop, and then they would form on top. That's the way we typically think of it, right? Makes sense so far? Take the hose, blow in it, bubble, 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 bubble. Okay. So, while that's happening, if I were to say, no, I don't want the gas to go into the container and rise to the top. I want the gas to come into the container and stay in the liquid. I want this to actually be contained into this liquid. How is that going to happen? Well, what's happening is that the gas is going through here. It's far apart. When it gets into liquid, I've got to find some way for these molecules of gas to be more attracted to one another. I've got to bring them closer together. I've got to slow them down. I've got to stop them from moving out of the liquid and going into the gaseous form. Now, thinking of an aquarium, for example, does anybody in here have fish or have kept fish? Okay, so if you have fish, why do you have an aquarium pumping air through a little tube, and maybe you have one of those, stones at the bottom that break it down into even smaller bubbles and have it rising through the aquarium? Why do you do that? What's the purpose of pumping oxygen into the aquarium? So what do fish breathe? What's the primary gas that they need to live? Oxygen, right? Rather than lungs, they have gills. God has designed them with an apparatus that removes oxygen from the water. Now, do you think the fish are taking water, H2O, breaking it down into oxygen and hydrogen, and then bringing that oxygen in and exhaling the hydrogen? If that were the case, we would continually have these little explosions on the top where the hydrogen gas was collecting. You wouldn't be allowed to have aquariums in your home because you'd have a hydrogen bomb down there. Okay? Don't get it near the water heater. What happened? The house blew up. Why? They had an aquarium. Oh. And they let it get near the water heater, right? Yep. Okay. That happens all the time. No. That fish don't break down water to get hydrogen and oxygen. They get the oxygen out of the water. What does that mean? That means there is oxygen dissolved into the H2O. And that the gills are able to take the oxygen out of the water, not break down the water. They don't decompose water. They are able to filter, think of it that way, they're able to strain out the oxygen that's dissolved in the water. So the water, or the air being pumped into your aquarium has several purposes. Yes, it helps nice rotation of the water. What does that do? It brings water to the surface where it can be in contact with the air, which has oxygen in it. That helps to oxygenate the water some. Okay? It also helps in that circulation to keep the temperature nice and even. Okay, so as the water's moving, it goes past your heater and makes the water be the same temperature. But the primary reason is that when you pump air into that liquid and it bubbles up through the aquarium, some of that air goes into solution. It dissolves into the water in your tank so that your fish have adequate oxygen to breathe. So in this process, as the air comes up through that air stone, it has a lot of dynamic motion, it's movement, it's air, it's a gas as opposed to the liquids. And in order for it to stay in solution, the molecules of the gas have to be drawn tighter together. There has to be enough attraction there to bring them in tight, to bring them in close, to basically bring them into a more stable situation. They're not as dynamic, they're not as full of motion. So again, just reading here, the solvent molecules must be attracted to the solute molecules. In this case, the water has to be attracted to the oxygen enough to pull the solute molecules, the solutes of gas. So in order to pull the gas closer, the gas molecules closer to one another than they were before. You can almost think of it as the solvent acts as its own kind of a magnet. It has attractions to the gases, The gases are out here. Maybe these two hands represent two different gas molecules. Think of my body as the solvent, and here's the solute, the gas, right? The attraction has to be such that I take those gas molecules that are out here, and I've got to bring them tighter together. When I bring them tighter together, think of it this way. I'm moving them, in a sense, from being a gaseous form to being what? As they become closer and closer together, what phase are they approaching? They're approaching a liquid, right? So the function of the solvent in a solvent with a solid is to bust it up. A solvent with a liquid solute is to kind of move between. And the function of a solvent with a gaseous solute is to pull them closer together. So it's exactly the opposite of a solid. One more time. The solvent, when it breaks up a solid, tries to get inside and pull them apart. The solvent, when it's a gaseous solute, is trying to get the gas to come closer together. If it doesn't bring them closer together, what happens? It just all bubbles out. It just all passes straight through. The part that dissolves is the part that does get pulled tighter together and stays in solution. That is the last teaching point on page 354 before it turns you over to the table on table 10.1 on page 355. So, 2 days just on the general nature of dissolving. Dissolving solids, dissolving liquids, and dissolving gases. In the case of solids, two different forms, ionic and covalent. The solvent in that case is trying to bust it up. For an ionic, it can bust it up all the way down to the ion. For covalent, it'll bust it up all the way down to the molecule, but it can't bust it up anymore. In the case of a liquid solute, the solvent just gets between them more than they were before. Since they were already relatively far apart, they just have to kind of mix together. But for a gaseous solute, the solvent has to be able to pull them tighter together. And by pulling them tighter together, they can stay in solution. But if the solvent doesn't have the force to pull them tighter together, then the gas simply moves based on density. In most cases, it's going to be less dense than the liquid. It's going to move out. It's going to come to the top, like this, instead of staying in solution, like this. Okay. So any general questions about dissolving? Those different cases? We're going to just very quickly go over the review questions then, if there aren't. We don't have any on your owns to work. Again, this is conceptual. So just the concept. That's why it may not be crystal clear now, but we're going to do a couple labs, and you'll see this. I think one of the labs actually is taking soda and then putting it in hot water, putting it in cold water, and see what happens to the bubbles. You know, what's the response of the gas in solution to different temperatures and things like that. Since everyone has turned in the homework, question number 1 says, when you dissolve sodium fluoride in water, which compound is the solute and which is the solvent? So it's sodium fluoride. What's the formula for sodium fluoride? Come on, we can do this, right? Sodium fluoride, is it ionic or covalent? It's ionic, right? So we've got sodium and fluorine, making the fluoride. It's a column 7 just like chlorine, so it's easy, right? There we go. It's done. Sodium fluoride. When you dissolve sodium fluoride in water, your answer's right there, isn't it? When you dissolve something in something, the something you dissolve is the what? Solute, and the thing you're dissolving it into is the solvent. Right. So when you dissolve sodium fluoride in water, which compound is the solute? Sodium fluoride. And which is the solvent? Water. Number 2. Contrast the way ionic compounds dissolve in water with the way the polar covalent compounds dissolve in water. Okay. What's the difference there in the question? Listen to it. Contrast the way that ionic compounds dissolve with the way that polar covalent compounds dissolve. Generally speaking, what's the answer? What's the difference between those two things?
Well, the covalent solvents are separated in their individual
Right. So the fact that it's polar covalent, what they're getting at is we're going to be dealing with the charge differences, right? Dissolving has to do talking about the charge differentials. So that's key to dissolving, understanding what dissolving is. So the basic question here is, what's the fundamental difference between how an ionic dissolves and how a covalent molecule dissolves? Right? We've covered that many times today. An ionic dissolves down to the individual ions. So in this case, sodium fluoride, when it dissolves into the water, like review question 1 said, it's the solute, it goes into water. What does it dissolve down into? If I'm in Frizzle's bus and I go all the way down to the molecular level, what am I going to see in solution? I'm going to see water, and within that water, what are the different components I'm going to see floating around? Sodium ions and fluoride ions. I'm going to see Na pluses and F minuses. And around them, I'm going to see why would I see the fluorines by the hydrogens? Because they have partial positive charges, right? And fluorine has a negative charge, so they're attracted that. Why wouldn't I see a fluorine hanging out with oxygens? They're repulsed. It's like elementary, get the guys sit by the girls. No way, they have cooties, right? Cooties. So the fluorines don't want to be over here. Why? They're so negative. But yeah, so are you. Yeah. Okay, so don't blame them. It's you too. Over here, so we got sodium. What would sodium say? I'll hang out over there. Why? Well, I'm positive. I can handle the negativity of that negative side, right? I can handle it. So at the molecular level, we're going to see water with fluorine and sodiums free floating. They haven't reacted. There's no bonding taking place here. It's just a kind of casual attraction. They prefer to hang out. They prefer to hang out here as opposed to there. And fluorines say, that's fine, I'll take those spots, you take these spots, and they work it all out together. That is sodium fluoride dissolved in water. What would I expect to find maybe on the other side of this fluorine? What does it want to hang out with? Another hydrogen, right? So you tend to see all the molecules start forming all these different relationships based upon their charges. So this is the sodium and the fluorines breaking down into the individual ions. But if we had the polar covalent, like the pH3 molecule, in water, it's still going to have partial charges. But the water is not going to be able to break the bond between the phosphorus and the hydrogens. It's still going to find its partial charges. It's still going to set up its orientation. This is still going to be the negative side over here above and positive side down here. When water comes in the vicinity, the positive hydrogens are going to want to go here towards the negative, and the negative oxygens are going to orient towards the hydrogens. It's still going to have that partial charge attraction. But we're not going to see the phosphorus and hydrogens become free floating. They're not going to break up. Why? The physical bond is too strong to allow water to get between them. They're not going to allow it. They're going to hang together as a family. Okay? They may be separated from the extended family, but they're going to stay together because the solvent doesn't have the strength to break that up. Because remember, when we're dissolving, here's the key. When we're dissolving, we're not creating a chemical reaction. We're creating a physical change. It's not a chemical change, it's a physical change. What does that mean? Fundamentally, nothing is reacting with anything else. Things are just being separated from one another. That's why dissolving an ionic doesn't represent a chemical change. You still have sodiums and fluoride together in the mixture. They're just not immediately next to each other like they were when they were a pure substance. When they were a pure substance, they could be bonded right next to each other. Now they've got water that's come between them. But they haven't reacted with anything. No new bonds have been formed. No other close relationships have been formed. And when the water leaves, everybody goes back to being what they were before. Over here, even more so, nothing changes, except water gets between the individual molecules. But there is no fundamental change that's made to the molecule itself. These hydrogens stay in place, the phosphorus stays in place, the electron sharing stays in place. The only thing that happens that's different is this molecule is no longer next to another molecule that's just like itself. It's completely surrounded by the solvent. In this case, it's completely surrounded by the water. I can't make it more exciting than that without, maybe blowing something up. I'll try to come up with a neat lab that shows this in an explosive manner. I think the explosions over the aquarium would probably work pretty good, wouldn't it? If I bubbled hydrogen through and said, if fish were pulling the oxygen out, this would all be left, and we'll just have a candle on top of the aquarium, and every now and then, quick little explosion to clean out the hydrogen. I mean, there's a market for that, right? Little igniter for your aquarium to keep the explosion small. If the igniter ever fails and it gets too much hydrogen in there, then it blows the house up. But as long as you control it, and then you can get a heat exchanger and take the energy and heat the home with it. I mean, there's all kinds of market here. You just figure out a way for the fish to be able to remove the oxygen from the water. But they don't. They're not making a chemical reaction. All they're doing is removing the water molecules from around the oxygen so that they can extract it.